Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I'm going to be working on and trying to repair this IBM PC XT motherboard. Well, it's a clone motherboard. This is the motherboard that I regularly use on the channel for testing purposes and tinkering and stuff like that. And I went to go use it today, and it wasn't working. So on today's video, I want to try to figure out exactly what's going wrong with this motherboard so I can get it working again, and I want to bring you along for the journey. So without further ado, let's get right to it. Now, I've done work on this motherboard on the channel before, and I've definitely shown this motherboard on the channel before. In the past, I've had to do some repairs, and I think it was one of these chips that was bad. It had something to do with the DMA control channels, and specifically when I tried to boot this thing into MS-DOS, it would not work when using a floppy controller. Now, this motherboard, which is totally just a clone, just says revision 2D, XT16-2 640K. This is a non-turbo motherboard, meaning it's just 4.77 megahertz. It works pretty much identically to IBM's 5160 motherboard. So it's got 8 slots, CPU, which is an 8088 math processor. It has a few oddities over the IBM, like an extra spot for another power connector. Not sure what that's all about. And we do have a couple options here for different ROM configuration. This machine normally would have had an 8K BIOS in this position, but I actually have a 1 ROM in here. It's a 28-pin 1 ROM. And that allows me to quickly load different types of ROMs in it. And I recently had a video on one of these on the main channel where I did some ROM or BIOS hacking on my actual IBM PC 5160. Currently in the main position or the first position on one ROM, what's in there is GlaBIOS, but the super fast version of it. This is the version that I modified on a recent main channel video that allows the IBM PC XT or regular PC as well to boot super fast. And if you haven't seen that video, just too long didn't read, was that basically I disabled all the diagnostics that would happen when you power on the computer. I mean, everything that happens, and it will just start the boot process immediately without doing any checking to make sure things are working properly on the motherboard, which can result in IBM PC booting up super duper fast. In fact, if you disable the floppy drive subsystem entirely, this boots into ROM basic in like 1.2 seconds, which for an IBM PC with 640K of RAM, that's very fast. Now, last time I was using this motherboard with 1 ROM and the super fast GlaBIOS on here, it was working totally fine. You would turn it on, it would just boot directly up into DOS or whatever was going on, or BASIC if you had no boot disk. And that is what's not working anymore. So let me get this hooked up so I can show you exactly what it's doing now so we can get to the bottom of what's wrong with this board. For testing purposes, I have the motherboard hooked up to a power supply. I have a little speaker hooked up so we can hear any kind of beep codes, and I have an IBM CGA card hooked up to the RGB to HDMI. Now, this is the modified CGA card that I've shown a bunch on the channel recently. I modified the card by cutting a couple traces, added some baud wires that essentially disabled the ability for the computer, the BIOS code, to disable the video output on the card. It has the side effect of the fact that when you first turn on the computer, instead of seeing just a black screen until the video card initializes, you actually see just some garbage essentially, and that's just the CGA card in its default power on state. Once it gets initialized, you'll get a normal black screen. But the other thing is, normally on 80 columns mode on a PC, when you type DIR or any kind of scrolling, the BIOS will turn off the video subsystem entirely. And that's because the way this card is designed, you will get snow due to contention with the CPU accessing the video RAM and the CGA card itself accessing the video RAM. For me personally, I'd rather it just have some snow while it's scrolling instead of the whole image kind of flashing, which is really kind of aggravating. And that's one of the things about the CGA card, which is kind of sucky. The flashing doesn't happen when you're in 40 column mode. It's because half the bandwidth is being used when it comes to the CGA card itself accessing the RAM. So the CPU and the CGA card are able to share the RAM properly. But 80 columns, obviously there's more being displayed on screen in every frame, and that's where you get this contention issue with this card. Later CGA cards from other manufacturers did away with the flashing by having dual ported RAM or faster memory access from the card so it could interleave with the CPU. But the original CGA card, I think from 1981, yeah, still a problem. Okay, so this is what's happening now with this system, with this fault, whatever's going on with the system. So let me turn it on. Here we go, 3, 2, 1. So we get a quick beep, and that's it. Nothing more is happening. And if I reset the system by shorting the reset pins, it just does the same thing. Quick beep, and we have this garbage screen. Now, normally what should be happening if this thing were working properly is you'd hear that beep, that quick beep, and then after, I don't know, a second or half a second or so, that garbage would go away. You'd have a black screen, and then it would show 640K at the top, and it would start booting the system. Now, I don't have anything that makes the system bootable installed into here, so it could be falling into BASIC, but it's really hard to know because Well, we're not really getting any feedback visually from the CGA card. Now, there's a couple things we can glean from the fact that it is making a beep, though, is that the system is executing code. If the CPU were not working or the ROM was missing, for instance, the one ROM wasn't working, the system would look the same visually. You'd have that garbage, but you wouldn't actually get a beep. And I can demonstrate that by just removing the one ROM from the system entirely. And I'll show you exactly what it does at that point. Okay, and now when I turn on the system, we get the same exact garbage. It looks identical, but no beeping. And that's, of course, because there's no ROM. It can't possibly beep. This is executing code with the CPU and causing it to beep. Also, we can glean a couple other things. AT power supplies, and this is an ATX power supply, but it's the same. It sends a power good signal to the motherboard, and if that power good signal is not making its way to the motherboard, then the computer never comes out of reset and never starts executing code. So the fact that we're still getting that beep tells us it's executing code. So the power supply is certainly good. We have the system coming out of reset, so the reset circuit is working, and the fact that we're getting that correct beep, and that is the duration that it should be, means the clock circuitry on the motherboard almost certainly is working properly as well. So I'm not really going to check the clock or the power and that stuff, because pretty much the system is showing that it's able to execute code. We're just not getting any visuals. So, okay, so now we have to kind of think about what might be wrong. Now, I can tell you that I've already moved the VGA or CGA card, I'm sorry, to different slots, and that doesn't really make any difference whatsoever. So I just moved it over one, and if we turn on the system, exactly the same. Same beep, same everything. Now, that could tell us that maybe this card is the problem. That could be quite possible. This card was originally battery damaged by a leaking battery. I found it in a pile of trash, basically. It was trash picked. But just in case, I'm going to grab another card, and this is a CGA and MDA card combo. So I'm going to set this to CGA mode, and we'll try this one out. Now, this one doesn't have the flashing or snow problem that the CGA card has, but also it won't display anything at all. Oh, actually, maybe it will, because actually I think this card does display kind of garbage as well. Maybe not the same garbage as the CGA card, the IBM one that is, until it gets initialized. But let's see what happens. Okay, that's right. That's what this card does. It does this flashing thing. But we're still getting the beep and we're still getting the flashing, so this card is definitely not being initialized either. Now here's another test. Here's an 8-bit VGA card. So this will need to have a switch changed on the switch block, because this is currently trying to initialize a CGA card, because these are initialized by the BIOS themselves, while this card has its own ROM BIOS on it. And the BIOS routine, when it's set for EGA or VGA, it just goes to execute the BIOS code that's on this, which is kind of like an option ROM, so to speak. It's just in a different location that's fixed. And that will initialize whatever card you have in there. It's pretty smart thinking on IBM's part, to be honest, because originally that was designed for the EGA card. But once VGA came out, it just used the same functionality. And that way, even though the card is architecturally completely different than EGA, the BIOS that's on here can be customized to initialize this VGA chip specifically, to put it into the correct modes, initialize the registers or whatever. That way the motherboard's BIOS doesn't need to know about the functionality of this card. And that's really how you can plug a newer VGA card into something like an IBM PC, and it does work as long as it's 8-bit. So let's turn on the system. Okay, now you just heard that it made the normal beep sound, but we don't have any initialization. Now there is something I do need to change. Okay, so I am on the correct input for the VGA connector that's on this. We do have to switch one of the switches on the dip switch block to tell it to initialize its video card, because right now I think it's trying to initialize the CGA card still. So it happens to be switch 6. If I switch this to the other position, now it's going to initialize any EGA or VGA card on the motherboard. And let's turn it on. So it beeps normally. We don't have a working display. Now here's a good test. With GlaBIOS, if you pop out the card, so I have no video card, but I have it currently set for EGA and VGA, I think that should cause it to beep. Yes. So that's a beep code that's basically saying, hey, I can't find your EGA, VGA card and initialize it. Hey, fix the situation. What this tells us, of course, is that GlaBIOS is executing code. It's able to know, hey, I can't find the option ROM that's on this VGA card, and I'm going to be unhappy about it. And that will only go away if I put a CGA card back in and change switch 6 down to the off position. So first we'll leave it on, and you'll hear a beep. Okay. Same beep code. So now I'll flip switch down, or switch 6 on, and there we go. Now it's initializing the CGA card. Well, or it would, but clearly it's not getting to that point, because looking at the video output, we have that same garbage that we had before. Okay, so that gives me some good ideas that I know it's not a video card problem, period, right? We've tried all the different video cards. I know for sure that the system is executing code because it's able to detect what kind of video card's in here, and it's doing that correctly. In fact, it's able to read the dip switches as well, because I can switch that between CGA and VGA, and it does what I would expect. But yet, why isn't it initializing the video? What's going on exactly to keep it from initializing the video? And what's even more strange, actually, is if you think about it, when I have it set to EGA VGA mode and I plug the VGA card into it, it's obviously able to talk to the card, so it's able to read the registers, it's able to see the ROM, because otherwise it would give us that beep code that it says, hey, I can't find your EGA VGA card. So that kind of tells us that the CPU is able to access the ISA bus based on code that's in the ROM. So with a few minutes of swapping some stuff around and flipping a few switches, we were able to use process of elimination to rule out that several different things are potentially our problem. Because just like with the Commodore 64, when I try to fix one of those, this is very similar to the black screen issue we get with those. It just happens to be that with GlaBIOS, the modified super fast version I have on here, it beeps when you first turn the computer on. So that actually gives us some feedback that we might not otherwise have. So even without a multimeter or an oscilloscope, you'd be able to at least get some information on the fact that your computer was executing code from the ROM. And that's a huge thing. That's a big deal and a big first step as to what might be the problem. So now is where the one ROM comes really in handy. Because potential issues that could be keeping the system from posting are maybe we have a RAM fault in the first bank of memory. On the IBM PC, when the BIOS code starts to run, it absolutely positively needs the first 16K of RAM to be working properly. And if that's not working properly, you're going to get very unpredictable results. As a test, let's just pop out one of these RAM chips, and these happen to be bank 0. In fact, it says 0 right on the edge of the motherboard here, 0, 1, well, it says 2 and 3. That's odd, isn't it? I don't know what that's all about, but I'm pretty sure this is going to be the first 16K. Without this RAM chip in here, and these are 256 kilobit MT RAM chips, and yeah, even though they say MT on them, don't worry about it. These are the reliable ones. Without this in there, that first 16K of RAM is going to be bad. And I actually don't know what's going to happen. I don't know if the GlaBIOS is going to freak out and not even do the beep code stuff now. So we'll just try this without the video card installed. We don't even really need it. So it does that. And I don't know, for fun, I'll swap this switch over to VGA EGA mode. And yeah, it just beeps. Solid beep. Now, it goes without saying that you can have all sorts of faults in your memory, and it's unpredictable what might happen if your first 16K of memory is bad. And the fact that when I remove the chip here, it just does that long beep, doesn't mean that's what would happen on your system. And of course, that's going to differ depending on what BIOS you're going to be using, because the BIOS is able to run. It's going to start to execute code. But where the problem starts to happen is it's going to start to use some of that memory for like stack stuff. And of course, the stack's not going to be working, the processor stack that is, so it's going to like push and pop stuff on and off the stack, and that's not going to work. And that causes very unpredictable results. So if part of your 16K has like some bits that are bad or mostly good with the occasional bad location, then again, maybe the system will work, but then act unpredictable. But removing that chip just ruins the whole first 256K of memory. And essentially, the ROM BIOS code just doesn't really behave correctly that way. Now, all is not lost, though, because there happens to be a ROM that you can load onto your IBM PC and the PC XT that does not need working RAM for it to actually work. And it's this, the XT RAM test. And I know I've talked about this a lot lately, but this is a RAM test ROM for the IBM PC and clones. And this was written by my friend David Giller. It's on his GitHub repo. And here's a screenshot of it. And if you've watched my channel on any of the PC repairs, you will have seen that I have used this particular ROM. And what I love about it is, as I mentioned, you don't need to have any working RAM for this to work. And that's because when David wrote this, he did it in a way that did not require the main memory to be working. So he very cleverly uses the video memory on the CGA or monochrome card, MDA card, for the processor stack and other temporary memory locations. A lot of the routines are unrolled, meaning they don't use JSRs like jump subroutines and stuff like that. They're just using jumps. And then once the memory inside the CGA card and the MDA card is validated to be good, then it just uses that as its temporary storage. It's incredibly ingenious, and it means you don't need to have any working motherboard RAM. So this is an 8K ROM, and I just have loaded this into one of the other locations on the one ROM. And the way you configure this, if I pull these jumpers off, is you can install these jumpers to have different ROM images load without me even having to flash this again. And what's going to happen here with this set to this jumper is when I power on the system, it's going to run the code for XT RAM test, which will immediately start looking at the video card memory and checking it. So it does a march test on the video RAM. And if it's good, it will initialize the video subsystem and then start executing the main memory RAM test on the motherboard. Now, if there's a problem on this motherboard due to the bus transceivers talking to the ISA bus, well, we'll know that pretty quickly when it can't initialize the video. Here we go, 3, 2, 1. Oh, there we go. It initialized the video perfectly. So this tells us a ton right here. A, we know the CPU is able to talk to the ISA bus properly. It's also able to talk to the RAM because it's currently going through the march testing of the main memory, and there's no errors so far. If I took one of those chips out again, like I did a moment ago, in fact, let's just do that. We'll just take out a random chip here. Has to be one that's not parity, by the way, because I don't think it tests the parity memory chip. So we'll turn that on, and it's going to initialize real quick, but right away it detects that first bank has a problem. It's going to be these first 4, right? Because 256K, that chip that I took out. So all of the later memory in the system works completely fine. It's just this first bank is the problem. And actually, what's kind of funny, you know, the motherboard's labeled incorrectly. It says 0, 1, 3, and 2 along the edge here. Well, I can quickly figure out where banks 0 and 1 is, which will be the first 512K, versus 2 and 3. So let me take a chip out of what is labeled 2 on the motherboard, and let's see where that ends up being as bad memory. It should be in the very last little section there, between 576 and 640. That is where this bad memory should exist now, if this was bank 3. But if it's bank 2, like it says, it's going to be in that upper section between 512 and 576. I know I'm on a tangent here. Oh, yeah. Okay, it's exactly like I thought it was. The last row of chips on here is actually bank 3. It's not bank 2 like it's labeled on the board, it's bank 3. Anyhow, with the chip back in there, we can see that the RAM test is working, and this tells us so much. This system is operating quite well. But now the question is, why isn't GlaBIOS initializing? That is the question. Why don't we try another IBM PC XT clone BIOS? So I went looking around and I found the AMI BIOS. It's a XTI AMI BIOS. It was used on all sorts of clones. And I have that loaded onto this, and it's loaded when I have the jumper in that position. So let's see what happens when I turn on the system now. Okay. Oh, yes, look at that. So it initialized. I mean, we know the system is able to initialize the video. This initialized the system, but now it's hung. I mean, I would assume, I've never used this BIOS, but I would assume it'd be counting the memory, it'd be doing something, but it's, you know, not doing anything here. It's just sitting here and dead. So I think that means we need to jump over to the ROM that I really don't like to use, the SuperSoft Landmark Diagnostic ROM. And the reason why I don't like this ROM is that the version for the IBM PC and PC XT has absolutely abysmal RAM testing. So if you have RAM faults on your system, this is a terrible ROM for using, which is really why I hit David up to write the XT RAM test, because I wanted something super comprehensive where you could very quickly see where your RAM faults were on your PC, and this ROM does not do that. But this ROM, on the other hand, does do a bunch of other diagnostics, so it is quite useful to try out. And at this point, we need a little help just to try to figure out what might be causing the system to freeze, well, for the AMI BIOS, where it gives us that, you know, freeze after it initializes the video, or for GlaBIOS itself to not even initialize the video. And we do have a copy of the manual. It says here, Landmark Research. So I guess what happened is this was made by SuperSoft, and I guess Landmark ended up buying them. So it tests out your CPU logic, it tests out timer channels, DMA, parity detection, 16 memory or 16 kilobyte critical region memory. So that's that first 16K of RAM. I don't think it will do much more. If that is a problem, I think it halts at that point. We know that memory works because XT RAM test showed it to be good. It tests that your DMA refresh is working. It looks for the interrupt controller, hot interrupt, interrupt level 0, non-maskable interrupt, MDA, CGA memory, you know, it goes on from there. Let's see what happens when I try to run SuperSoft on the one ROM, and I happen to know it is when I put 2 jumpers on like that, that is the SuperSoft configuration. And I'm fully expecting this to initialize the video and hopefully get to at least the 16K of a RAM diagnostic test there and go beyond. And maybe this will give us a clue as to what's wrong. Okay, it's going pretty quick. 16K critical memory region. Oh, yep, memory refresh. I think what this does is it's checking to make sure that memory values aren't decaying. The DMA controller is required for the memory refresh to be working properly on a PC. So if the DMA controller is somehow screwed up, like DMA channel 0, I think it is, then you might have memory issues. Then we have interrupt controller passed, hot interrupt passed, interrupt level 0. Ah, okay. It's just stuck here. I happen to know from previous experience, when you run this test, it goes by pretty quickly on that test. I'm going to reset the machine here. So let's reboot it. Well, that's our first clue as to what's going on. Right there. Interrupt level 0, froze again. Okay, great. Well, now we finally have something to go on. And it was definitely very helpful to have the one ROM, because I could try out different ROMs on here very quickly and easily and be able to see, well, you know, what might be the problem. And we could start ruling things out. Now I'm kind of curious. I want to go back to the AMI BIOS that does initialize the system. And I want to see if it's, and whoa, look at that. Okay, so that kind of confirms this interrupt error thing. We didn't see this last time. Let me reset the system. Remember, it just sort of hung there, but it's like it's able to detect that maybe there is some kind of problem with the interrupt. Now, we don't know like what this ROM is doing exactly to try to detect that. And look, it didn't work this time. So even though it worked that one time, it didn't work the first time, it worked the second time. Let's reboot the computer again. That's the CGA card. You can ignore that flashing that goes on. Oh, look, we got it again. So sometimes we get an interrupt error. Now, if I remove the jumper here off the one ROM and we reset the system again, this goes back to GlaBIOS. Oh no, it won't. I have to power cycle the whole computer. Power cycle the computer to go back to GlaBIOS, because those jumpers only affect this at power on. So there we go. We're back to what GlaBIOS always does. Gives us a beep and then nothing. So it kind of tells us that whatever this interrupt problem is, something about GlaBIOS must be trying to use that interrupt before it initializes the video, and that's why we're getting nothing. Okay, so one thing I did not do is this thing has a good number of chips in sockets. All of the RAM is all in sockets and our ROMs, but then we have additional sockets, and I know some of them were ones I installed, because I can see they're the round hole type, like these two. In fact, I think this chip right here is the programmable interrupt controller. This is what handles interrupts on the PC. And this chip here in the socket, I forgot what this one does exactly. Just giving it a good push to make sure it's in there all the way. This one is like a general purpose IO chip, I think. I forgot the name of it in like IBM speak. One of these is going to be a DMA controller. It might be this one, to be honest, because I think the DMA controller needs to be able to talk to all the address lines, and it needs to talk to all the data lines. And then this other IC is probably our PIT, our programmable interval timer. And even though it's got an NEC part in here, and so does this one, these are all just sort of clones of the Intel chip. So 8255, 8237. This one here is an actual Intel part, 8259. And this is going to be an 82 something as well, maybe like an 8254. It's just NEC changed out their part numbers a little bit. But anyways, what I wanted to say is that there are some sockets on here. So maybe I need to push down all the chips that are in sockets. So we have these two chips. We have the CPU itself. Give that a good push. And this is the, what does this one do? I forgot what this one does. I think it's something to do with the clock or something like that. And so is this one up here. Oh, and then we have an LS245. Okay, so I gave those a push, and maybe I should have done that sooner. Let's see if that made any kind of difference whatsoever. None of those chips were particularly loose, so I'm not expecting anything to really change. No, no change. Okay, good. So we really do have a fault on this board. So I talk a lot of crap about this SuperSoft ROM, but to be honest, in this case, it has really provided us with the most useful information. And let's go to the manual to see what it says about the tests, especially for the interrupt controller test and the interrupt 0, where it's getting hung up on, so we can see what it's trying to do that's causing it to freeze. So the 8259 test talks to the registers to ensure it can be initialized and data can be written to it and read from it, because it is a device that can be read from. Function of the 8259 interrupt controller is to prioritize hardware interrupts, providing arbitration between external interrupt requests from devices on the bus and the CPU. The 8088 CPU, incidentally, only has one interrupt line, just a normal interrupt line, and you need to have an external component like this to arbitrate any additional IRQs. So channel 0, aka IRQ0, is used for the real-time clock update. Channel 1 is used to indicate a key press, so it's hooked up to the keyboard. And channel 6 is reserved for floppy drive controller. Now, the rest of the IRQs aren't allocated by default on the IBM PC, so that's why you have like LPT and COM ports on 3 and 4, and you might have the Sound Blaster card on IRQ5 or IRQ7, because those are also available for use. Now, in the IBM PC AT, the 5170, what IBM did is they added a second interrupt controller and they cascaded it off of the first one. So I think it's IRQ2 on the first controller cascades to the second chip, and that gives us IRQs 8 through 15, which are available on the 16-bit ISA slots on that extra little piece. As for this particular test, though, on the XT, it's only going to test 0 through 7. That's all that exists. And it says if you have a failure, you're going to have a beep code, and replacement of the 8259 is recommended. Okay. Hot interrupt test. This one also passed. This test disables all interrupt in the systems, and then it enables interrupt to the CPU, waits approximately 1 second, and during this time, the CPU will record any interrupts that may occur. Because all interrupts were disabled, none should be registered by the CPU. The test fails if any interrupts occur. So I surmise what's happening is that there's an interrupt handler that's installed by the ROM, and the CPU is listening for an interrupt to come in over its pin, but the ROM tells the 8259, the interrupt controller, not to send any interrupts. It's called masking the interrupts. You can mask off any interrupts or all the interrupts, and if the 8259 is working correctly, or you have a good signal between the CPU and the 8259, then if any interrupts do come in, the CPU is going to see those when there shouldn't be any, and then that'll flag a problem on the system. That's what this hot interrupt test is. Test fails if any interrupts occur. Failure of this test is an indication of a problem with either the 8259 interrupt controller, the 8288 bus controller, or the CPU. Detection of a hot interrupt will cause a beep code and replace the 8259, 8288, or CPU and try again. This test, remember, is passing without any issue. And incidentally, the 8288 bus controller that I mentioned in the diagnostic there, that is this small ceramic IC. And this indicates that that chip being bad could potentially cause a hot interrupt to be generated. So that's kind of interesting. We'll have to look at the schematics to see how that chip comes into play. I could totally see the 8259 itself being bad, or the CPU being bad, or potentially like something in the trace, like if you have a bridge trace where some other signal is ending up on the interrupt line, then the CPU is going to see an interrupt when there isn't one because it's just some other data on the line. But yeah, 8288, not too sure about that one. Okay, well now we're going to go to our test we're failing on. This test checks to see if a time of day interrupt from channel 0 of the timer chip, the 8253, which is connected to IRQ0 of the interrupt controller, is able to interrupt the CPU. Furthermore, the test ensures that the CPU is interrupted at the correct rate. Failure of this test can indicate a problem with either the 8253 timer or the 8259 interrupt controller, or of course there's that 8288 bus controller, or the CPU. Replace those components in order, one at a time, and observe results. Failure of this test is reported by a B code. So if you've ever used an IBM PC XT, even if you don't have a real-time clock, you'll notice that if you set the time and date in DOS, it's able to keep track of the time pretty accurately while the system is running. And that is handled through this particular routine. So the programmable interval timer, the PIT chip, which is the 8253 that it mentioned, it called the timer chip, that has one of its channels, has 3 channels. One of them is connected directly to IRQ0 on the interrupt controller chip. And when the BIOS sets up the system, it initializes that programmable interrupt timer channel 0 to fire at a very regular interval. And that's going to trigger an IRQ0 on a regular interval. And it is that regular firing of IRQ0 that allows MS-DOS to keep the accurate time. Even if you're running programs and doing stuff on the system, it's able to keep that time because those interrupts are interrupting whatever program is happening, and the CPU is executing a little bit of code to handle IRQ0 to keep that time of day accurate. So presumably what this does is it sets up the programmable interval timer to fire at regular intervals, like it does when you normally boot the system, and that's hooked up physically to IRQ0 on the interrupt controller. And then when the interrupt controller, when it's set up appropriately and the interrupts aren't masked off, they're not disabled in that chip, what it does is it sends a signal to the CPU to say, hey, interrupt has fired. And then the CPU has an interrupt handler that is able to run. And the CPU does something, I think it talks to the 8259, like picks up what interrupt fired off the bus or whatever. I think they kind of work together on that thing. And then the CPU is able to then go and execute some code to handle the interrupt 0 function that's happening. Well, to me, it sounds like this test just sort of sits there and waits a little while for some short interval of time, and it expects that interrupt handler that's on IRQ0 to fire because that whole system that I just described should be working. And it seems to, well, the weird thing is it's just freezing. We see it just freezes. But it implies here that it's going to be able to detect if the interrupt is not firing. Like say there's a problem with the 8259, that's the interrupt controller, or the programmable interval timer, and it's not generating IRQ zeros. It seems that it's able to detect that, and it will give you like an error that says there's no interrupt. So something's happening where it goes to check the interrupt working, and then the system just freezes. So what's happening here with it freezing is not really shown in the results, but it does give us some ideas of like what systems are in play for this part of the function, being the programmable interval timer itself, the interrupt controller itself, the bus controller, and the CPU. So I think the next step on here is to break out the oscilloscope and the schematics for the IBM XT, just so we can see the pinouts we're going to be looking at, and take a look at the signals going from the programmable interval timer, which is this NEC 7154, which is the same as the Intel 8254. We should see channel 0 going to the interrupt controller, that's IRQ 0 input on this, and then this should have an output that then goes to the CPU to say, hey, the interrupt has fired, and when I guess I boot up the normal Glab BIOS, we should be able to see that stuff get all initialized, and then we should start seeing the pit channel 0 firing into IRQ 0, and then that firing to this, and we can kind of see, well, maybe what's going on exactly. And then I need to look at the schematics to figure out exactly how this bus controller here, 8288, has anything to do with any of this. All right, so I found the IBM technical reference for the IBM PC XT. Here we're looking at the ISA slots. One thing you can keep in mind is that it does not even route the IRQ for 0 or 1 to the ISA slots themselves. So a card plugged into one of these slots cannot affect the operation of interrupt 0 just because it's not available at all. And that's because, of course, interrupt 1, always used for the keyboard. Interrupt 0, always used for this programmable interval timer, time of day thing. And they would never be used on an ISA bus connector ever. That's why they're not there. And here we are on sheet 8. And there's the 8253. I happen to know this is the programmable interval timer. And this one happens to use the 8254, but I think they're compatible with each other. Those are the 3 channels that are output. And it's channel 0, as what we just read, should be the time of day signal that makes its way to IRQ 0. Oh, there, it says it right there. Okay, so I'm just going to spend a moment as I find each one of these. I'm going to mark it on the chip itself so we know where to probe with the oscilloscope. And one thing I want to make sure is that none of these signals make their way through any additional logic chips, because if they do, those chips could easily be bad. So IRQ 0 makes its way to page 1. And the way these IBM schematics work is the input stuff is on the left. There it is, IRQ 0. And that goes into the 8259 on pin 18. So on the interrupt controller, we can see all of those IRQ inputs, 0 through 7. It's hooked up to the data bus. It's got some CAS lines that aren't used, write signals, blah, blah, blah. But pin 17, the interrupt line, that is the output that should be making its way over to the CPU. Or is it this int A signal, actually? Which ones is it? It's funny how it's not labeled. I'm quite sure that's the CPU. This will be the math coprocessor down here. Now there's another signal int A that comes out of the interrupt controller, and that makes its way, where does that go? That goes over here to this chip. Oh, it goes to the 8288 as well. I suppose that's how they integrate together. Okay, well, I'm gonna have to look up the data sheets on these chips to see, well, what is this int A doing on there? But I also need to mark down which outputs we need to take a look at. Can't read this int A signal. I think that's a 26. All right, here we are on the retro web. Pin 26, interrupt acknowledge. Ah, so that's some kind of an input that goes into there. Okay. And also thanks to RetroWeb, here's the datasheet for the bus controller, the 8288. Pin 14, int A, that's the interrupt acknowledge signal that we're gonna have to look at. There we go, multi-bus command signals. Ooh, so I marked those chips, and let's go mark the CPU on the appropriate pin. There it is, int. Pretty sure that's gonna be pin 18. So to summarize, the PIT gets programmed channel 0 to output a regular interval that is going to go to IRQ 0. And it's that pin, and it goes to that pin right there with a single dot. And then the output of this is that pin and this pin. One of them, I think it's this one, the lower on pin 17, it makes its way over the CPU on that pin. And this one makes its way over to the bus controller on that pin there. Now, if I set the 1ROM to boot the system into the XT RAM test, there isn't going to be anything coming out of the PIT on channel 0. This should have no signal on there, and therefore nothing should be going into here, and nothing should be coming out of this and going to the CPU. All the interrupts are turned off, as well as the programmable interval timer, which is not used. When we run the SuperSoft ROM, on the other hand, probably there's nothing happening at all until it gets to the interrupt tests, then we should start to see some activity on here. And well, I guess we can look at them with the oscilloscope and see when the system freezes, what is the state of the signals. So I think I have some really good information. Let me get set up with the oscilloscope and let's start probing this motherboard to see what we can see, figure out what's wrong with this thing. Before we get started with the scoping, what I want to do is just check continuity between the various pins that I've identified. And I have this in continuity mode. So first we're going to check the PIT channel 0 to interrupt 0. That is connected. Now I'm going to check the output that goes to the CPU. That is connected. And I'm going to check the output that makes its way over to the 8288. That is connected. Okay. So just to confirm, we do not have any chips in between those bigger chips that could be bad, any TTL logic. So I don't have a CGA card in just because it's easier for me to test because I don't need to see it right now, but I have it set to run the XT RAM test. When I turn on the system, we should have that triple beep. Yep, okay, so it's running. So there we are, 1 volt peak to peak. We are at 4.77 megahertz on the clock chip on the CPU. I already knew the clock was good because we get a working system. I just want to make sure that it is. So let's check out some of the data lines on the ROMs. That's one of the address lines on one of the ROMs. That should be one of the data lines on it. And you know what, actually, I just realized because I don't have a CGA card installed in here, the test is not actually running. I think the ROM has halted. So I do need to keep a CGA card in here. So I'm going to use this 16-bit riser, and even though it's 16-bit, it will work as long as I put it somewhere where the little extra part doesn't hit one of the chips. It doesn't work in that socket, but it should work in this one. There we go. So now when I turn the system back on with the CGA card installed, the diagnostic ROM should run properly. Make sure everything looks good. Okay. And now when I take a look at the signals, like data lines and things, it should look a lot different. Yeah, I think what was happening was the diagnostic ROM XT RAM test was trying to use the RAM on the CGA card for its stack and stuff. And of course, that's not there. So we didn't have any kind of useful stuff. So this is all the normal activity. And if I look at one of the data lines on one of the RAM chips, yeah, it's in the middle there because it's going high impedance, because it disconnects the bus. The RAM on the PC is isolated from the rest of the system using bus transceivers, but the ROMs are not. So that's why there's plenty of activity here. Yeah, okay. Anyways, point being, now with it running, if we take a look at the output of the programmable interrupt timer, we shouldn't see anything. Oh, well, I stand corrected. There is something happening here. Let's reset the system and see how long that takes to appear. Huh. So even resetting the system, that doesn't go away. But if I turn it off, it just instantly shows up. Well, this particular signal, which happens to be happening at 18.2 hertz, is coming out of the programmable interrupt timer, and it is making its way into IRQ0, which is that, because we know it's physically connected. But let's check the output of the interrupt controller, the one that goes to the CPU, because I do not expect to see anything happening there. We'll just see a bunch of typical TTL noise. I'm going to put the trigger up there. Yeah, that's just normal activity. And if I reset the system while it's in reset, but yeah, that's not a problem. This is all way up near 5 volts, so completely fine. But as I said, the input to the interrupt controller, it does have output coming from the programmable interval timer at whatever, 18 hertz. Okay, interesting. So the reason why if I go on the CPU, there's actually nothing going to be happening on the input pin, that's simply because all of the interrupts on the programming to the 8259 interrupt controller are masked. They're disabled. So it's not even sending any interrupts over to the CPU, period. And consequently, I assume if we take a look at the other output, which is this one, this is coming from the 8288, the bus controller, nothing's happening either. There's no triggering going on whatsoever. Now what I'm going to do is I'm going to keep the probe on the output that goes to the CPU, and we're going to switch over to GlaBIOS. So I just take the jumper off the one ROM and turn on the system. We should see something on here. And we do. Wow, we saw it like once. And then it was just gone. So we'll change to normal trigger mode. Yep. There we go. So we had a few triggers. Let's do that again. I just want to see how many of those triggers we're getting before the system kind of freezes. Interesting. Every time I hit the reset, it kind of changes a little bit. Let me turn the power off and on. So power's off, power on. Because if we take a look at the schematic here, input onto the CPU just says INTR and doesn't have a line over it. So it's actually asserted when the signal is high. So this is opposite to what we're used to on like 6502. It is not active low, it is active high. So right here is where it's getting triggered, because I'm pretty sure what we're looking at this way. All right, yeah, I think what's happening here is like the system comes out of reset, essentially right there. Again, things get initialized. And then what's happening is the programmable interrupt controller is getting turned on, the PIC is getting turned on, and then it's sending interrupts to the CPU, which is what we were seeing there. And the buffer is not very big on this oscilloscope, but if I power cycle the computer, you can see it's like we get 3 interrupts, 3.5 interrupts, and then the system just gets stuck. And power cycling the computer doesn't really change anything. Now, while it's frozen, if I go onto the pin for interrupt 0, we should see a continual waveform, just like we did while the diagnostic was running. And yeah, there it is. So this is just running at that 18 point whatever 1 hertz. And I'm thinking the reason why it does that on the XT RAM test, probably when David initializes the system, he just looked at some code that does it for the XT. He's not really super familiar with the PC XT, and he just copied that code. So even though the interval timer, I don't think it's used on the XT RAM test, I think it's just set up, and it obviously is not generating any interrupts, unlike GlaBIOS, which absolutely does, because this is trying to make a working PC. And there we go, we get our hit of interrupts, and then the system just sort of seems to freeze. Now what I'm going to do is I'm going to put the jumper on that's going to go to that AMI BIOS. Let's see what this one does. Interesting is it went low, so if I reset the system, and then there's a single pulse, and that's it. So let's see how big this particular pulse is here if I zoom in. There it is. It's just one little trigger. Now this is the AMI BIOS. Remember, that was freezing and occasionally give us that interrupt error. But the question is, where's this coming from? Let's look at to see if the channel 0 is set up. Yeah, it is. So what this is the 18 hertz. The PIT thing. Now remember, there are values that you can program into the interrupt controller where you can mask out certain interrupts. So you can tell it, even though you're receiving interrupt 0, like right here what we're seeing, don't send this over to the CPU. Only send other things to the CPU. So I have the jumper switched over to the landmark test. First, what I'm going to do is we're going to turn on the system. You'll be able to see what's happening. And I'm going to monitor the input to IRQ0. And we want to see when we start seeing the input where it's generating that programmable interval timer. Oh, look, it's already being generated now. What's kind of interesting is obviously the way the timer is generating these signals looks different right now than how it did with the other BIOS. The other BIOS was more like a normal square wave. This is a pulse, but it's still at the 18.18 hertz, which I guess is good enough. We are frozen though, just like we were before. And if I check the output of the interrupt controller, we don't have anything happening right now, but it's because it's in that frozen state. So I'm going to power cycle the computer, and because I'm on normal triggering, that's why it's not updating right now. So we turn on the system, it went high. My assumption is we're not going to see anything out of this at all until it goes to do that particular interrupt test. That's what I'm thinking. Because right now we know that that PIT input to IRQ0 is happening, but nothing is coming out of this chip. And I don't think it will until it does interrupt 0 test. And then we should start seeing this become active. Oh, there it is. So it went low because it like initialized that chip or whatever. And then we had that one pulse, which you don't have very high resolution of, and then the system crashed, or rather it froze. Okay, so that's the output from the programmable interrupt timer that goes to the CPU. How about we check the output on that chip that goes to that bus arbitrator chip, the 8288. So I'll power cycle the computer. We'll do the same thing here, and we'll just watch to see if we get that one pulse and then it crashes. Yes, there it is, one pulse. So this is the acknowledge pin, by the way, that comes out of this chip. The signal's coming from here and it's going into the interrupt controller. I think this lets this chip know, hey, the CPU received your interrupt request and it received the interrupt value, vector, whatever, that was put on the bus by this chip. And then this goes, okay, you're good to go. You can do the next interrupt. Like, I'm ready for the next interrupt. And I think that's what that acknowledge is. So we can see that it's, making its way around between these two chips, but why is the system freezing? Now I have an idea. What if I take this chip out and I disconnect the pin that goes from the PIT chip, the interval timer, that's the time of day. What if we disconnect it and we don't even have it go into this at all? And that way, it's not possible for IRQ0 to actually generate an interrupt. And because it's the right thing to do, I think I should hook it up to ground, which is going to be pin 14 right there. So that way it's not floating, that interrupt input. But I'm going to switch our view over to one where you can see what's going on. And I'm going to pull the jumpers off. So we're going to try to run GlaBIOS BIOS here with interrupt 0 disabled. All right, here we go. You ready? 3, 2, 1. So look at that. It posted. Now it froze, but it's quite possible it's trying to use the timer, which of course is not working anymore because it's disabled, to check the floppy drive, for instance, and stuff like that. So I'm going to flip switch 1, which happens to disable the floppy drive, and we'll power cycle the computer, and we'll see if this goes into basic, for instance. No, it doesn't go into basic. It still doesn't work. But we have an improvement. We have an absolute improvement. So let's try the AMI BIOS one. There it is. Oh, interrupt error. So it gave us the error. We've seen that before. Let's reset, see if this is reproducible. Okay, same thing. So maybe this is going to accurately give us interrupt error, because it knows, it should be getting the programmable interval timer interrupt IRQ0, and it's not happening. Okay, so that's regular. Let's try SuperSoft. There's no point to try the XT RAM test because that already worked. And let's see if SuperSoft detects a problem. I'm assuming we will get an error, just like we've been getting, but instead of it freezing, it's probably going to tell us that there's something wrong with interrupt 0, because obviously it's disabled now. Yep, got a beep code. It's kind of loud too. We figured out lots here. So we know for sure the programmable interval timer, the PIT chip, is working. It's generating the PIT signal to square wave at 18 Hertz properly. Okay, well actually that's all I've seemingly figured out. But we do know for sure that GlaBIOS BIOS must be trying to use the programmable interval timer, or the IRQ0 timer functionality, early on in the boot process before it initializes the video. And it seems like whatever's happening with this computer is anytime IRQ0 is fired, it seems to freeze the computer. Now here's the rub. Typically the interrupt handlers, so how an interrupt is handled, is set up by the software on the computer. So basically the BIOS sets up how IRQ0 is handled. And we've tried different ROMs, the AMI one and the GlaBIOS BIOS, and they're both freezing. And then of course Landmark also does its own thing, or SuperSoft that is, and it hits that IRQ0 and it freezes. It is able to detect that no IRQ0 is happening now that I have it disabled. So that rules out that the programmable interval timer is our problem. And what we saw on the oscilloscope is that when it is hooked up, we did have the correct signal going to the CPU and going to the 8288, and yet the system is still freezing. So it kind of screams to me that the problem is the 8288 or the CPU, because I don't see how it could be the interrupt controller itself, the PIC chip. The interrupt controller seems to be doing everything that it should be doing. I suppose the one thing it might not be doing is, from the best of my understanding, when an interrupt is fired, what it does is it sends a signal to the CPU, and the CPU in the next bus cycle goes to the data bus to pick up the value of the interrupt. Because remember, the interrupt could be 0 through 7. So I suppose actually that the interrupt controller could be bad, because maybe what's happening is it's not putting the correct information on the bus, and the CPU is waiting for it and just sort of sits there forever. It's hard to say exactly, because you need like a high-speed logic analyzer to really look at what's happening there in that interaction between the CPU and the PIC chip. Now on the motherboard, one thing that is good is, because of previous work that I've done, obviously the interrupt controller is in a socket already. So I can easily just swap this out. And the CPU is, and so is that. So everything's in a socket that we need to hopefully fix this system. So what I happen to have right here is a set of some XT chips that I pulled off of a dead or damaged XT motherboard. So this is like the entire chipset, I think minus the CPU, but I have plenty of CPUs we can test out. But I think in here we should have pretty much everything we need, like an 8288, so we have an extra one of those, that's good. And looks like right here, 8259, this is the interrupt controller. So I can test this in the system here, and we can see if this fixes it. I think our problem has got to be, the problem has to be one of these 3 chips. It has to be. I don't see what else could be the problem here. All right, I'm just going to unplug the jumper, so we're going to go to GlaBIOS BIOS, because that's the quickest one for us to tell. Turn it on. Nope. Sorry about the flashing. That comes from this CGA card. So that did not work. It would have initialized the video by that point. So we can tell pretty much for sure that this interrupt controller chip is fine. So put back in the original one. I guess next, should we test out the 8288? I don't really know how to test this other than swapping it over. It appears that I have to desolder these from another motherboard. So the pins they're kind of bent up and mangled a little bit. So they're kind of hard to get into these sockets. So we have the original CPU, the original interrupt controller, and now we have the replacement 8288. Okay, here we go. Is this going to fix it? 3, 2, 1. Nope. Sorry about the flashing again. So it's not this. I mean, that only leaves the CPU. How? How could the CPU be the problem? It's a really nice ceramic Intel CPU, an original 8088, not the Dash 2 variant, or I think it's the Dash 2 variant, the one that has faster clock speeds. So it's just a 4.77 megahertz part, and that is it, or maybe 5. I think 5 megahertz is what these are spec'd for. Went to my parts bin and found this nice Siemens part from 1988. I don't see these too often. Let's try this one. If this fixes the problem, this will definitely be the first time I've ever had an Intel 8088 processor fail, like one of these ceramic ones. Okay, 3, 2, 1. Is this going to fix the problem? If it doesn't, I'm not quite sure where to go from here. So here we go. 3, 2, 1. No, it did not fix the problem. I'm going to switch back to super soft. We will see what this does now. So it's not the CPU, it's not the 8288, and it's not the programmable interrupt controller. So what exactly is the problem? Especially because this motherboard obviously has no trouble reading the RAM, talking to any of the other peripheral ICs on the board. Look, frozen exactly the same way. I suppose what I should do is swap all 3 parts simultaneously, and we'll see if that does anything. So all 3 chips are swapped. Let's just take the jumpers off so we can see if GlaBIOS works now. I just doubt it. Nope. Same exact problem. And here's what I don't understand. It froze in exactly the same way. If there's something on the motherboard that's trashing the data bus, like there are multiple data buses because there's one for the RAM and one for the ROMs and the peripheral chips and stuff. If something's being trashed where the CPU can't communicate properly with the other things, how exactly is the system working to this extent? Like, is it able to run code? It's able to test all the RAM. That works fine. It's just the interrupt stuff that's failing, or at least interrupt 0 is failing. Like, how is that possible, especially now that I've swapped out the 3 chips that have to do entirely with interrupt handling? Okay, well, let's just take a look at these data bus things first as an example. So here's the 8088 CPU. The address and data bus lines, the first 7 are, so first 8 of them are multiplex, so it handles address and data. So we have AD 0 through 7. Now, if you look at the shaded area for AD 0 through 7, it makes its way over to this IC, which is a LS373, a latch. Now, this is what generates the address line, so A0 through 7, and this other LS245 is generating D0 through D7, so the actual data lines. And then as for the rest of the address lines, A8 through A19, those are not multiplex, so those just go through an LS244 and another latch. Now, as an example, when we take a look at the interrupt controller, that's D0 through D7, notice it's hooked up to this bus called XD0 through 7. So it is not hooked up directly to the output of these latches, which, remember, if we look at the labeling, is just D7 through D0. That tells us that somewhere on this schematic is going to be a bus transceiver, an LS245, that's going to interface those 2 things together. So over here on sheet 5, we're going to see the address lines, well, somewhere over here. There it is. So this is where the data line 0 through 7 gets converted into these XD lines. Now, looking at the XD lines to see what else they're used for, they go to a whole bunch of different sheets. It's used for the ROMs. So this is the 232K ROMs on the regular IBM 5160. I'm sure it's the same on this motherboard, and they don't really reinvent the wheel. They just change it up a little bit. And we can see here it goes to like 1, 4, 8, 9, and 10. Well, for sheet 1, this is what we looked at. The XD lines, they go to the interrupt controller specifically. And then they make their way over to this IC, the 8237. I think that's the DMA controller. Yeah, so it's got all DMA stuff on here. So that's the DMA controller. The data lines make their way over to this latch as well. This has to do with the whole DMA circuit, the way this all works. You know, I wonder if this could somehow have something to do with it, actually. Like, what if something here with the DMA controller is getting turned on when it shouldn't, and it's somehow stomping on the data bus, for instance? Okay, well, let's keep that in mind for a second. Now that's for the DRAM on the board. This is the DRAM. The DRAM does not use the XD lines. It goes from the data lines directly to the MD lines, the memory data lines. It looks like the XA lines for the addressing, that is used for the DRAM, but the DRAM uses a separate bus. So nothing in the DRAM section could have any negative effect on what's happening between the CPU and the interrupt controller, for instance. And we already know that the DRAM subsystem works totally fine because XT-RAM test has no issues whatsoever testing it. And then here's our last thing. So the 8235, this is the programmable interval timer. That is hooked up to the XD lines as well, and some of the XA lines. So that's understandable. And here's XA lines on the 8255. So this is, I think, for like keyboard stuff and I think RAM stuff and dip switches and stuff like that. It's all kind of controlled through that chip. And finally, the ISA bus itself does also use the X lines, at least on the original XT. So the XD lines and XA lines are there. Okay, so ISA bus, all the peripheral chips and the ROMs are on the XD bus, and then the RAM has its own thing, and then the CPU has its own thing when it talks to like the math coprocessor. So since I've already ruled out the fact that there's nothing wrong with those 3 chips we swapped, all I can think is that there's some kind of corruption happening when the XD line is loaded up with the interrupt value from the interrupt controller. The PIC should be setting up the bus to say, hey, interrupt 0 was called. And that's what the CPU, I think, is trying to read. We should go look at the data sheet just to confirm that. So on the data sheet for the 8259, it's a Mitsubishi data sheet, it says the call instruction to the CPU is generated automatically. I think this is what I was talking about, how when the interrupt is triggered, the next cycle after interrupt is triggered is basically this call instruction, which it gets put onto the data bus to say, hey, this is what you need to do. This is the interrupt that was triggered. And then as for the interrupt signal, this pin goes high whenever a valid interrupt is asserted. So this is the output that we looked at with the scope earlier. And then the interrupt A, the interrupt acknowledge, is an input. And when interrupt acknowledge from the CPU is received, the 8259 releases the call instruction or vectored address onto the data bus. Ah, that's interesting. So that's when it writes to the bus, when the interrupt acknowledge goes into it. And we see that signal going into it, right? We saw that. We should double check it to make sure. So, and then here's the sequence. When one or more of the interrupt request inputs are raised high, the corresponding IRR bits for the high input levels will be set. Mask state and priority levels are considered. So this is that masking where you can like turn off interrupts and stuff like that that happens in the interrupt controller itself. It figures that out, and then it sends the interrupt signal to the CPU. We saw that working on the oscilloscope, so we know that's good. Then the CPU acknowledges it with the interrupt acknowledge signal, right? So it pulses it back to the interrupt controller. And upon receiving that from the CPU, a call instruction is released onto the data bus. A call is a 3-byte instruction, so an additional 2 int A pulses are issued to the 8259 from the CPU. 2, so we should have 3 total, because it needs to put 3 different bytes onto the bus. I only remember seeing 1. These 2 int A pulses allow the 8259 to release the program address onto the data bus. The low order 8-bit vectored address is released at the second int A pulse, and the high order 8-bit vectored address is released on the third int A pulse. Corresponding to the interrupt request, input is set upon receiving the third int A pulse from the CPU, and the normally IR bit is reset. This completes the 3-byte call instruction, and the interrupt routine will be serviced. So I really think what we need to do is we need to validate that we're getting these 3 int A requests when we get that single interrupt 0 pulse out of the interrupt controller, because I don't recall seeing that. And I'm going to switch back to the AMI BIOS, because we know when we power on the system here, we get like a single pulse out of it. I was getting like a single interrupt 0 pulse, and then the system freezes, right? Okay, so what I'm going to do is I'm going to turn on the system, and the first pin that I'm on is the interrupt output from the controller that goes to the CPU. And this AMI BIOS, I think we should get a single pulse. There it was. There was our single pulse. Okay, there's our pulse, nice and clear. So now I'm on the other pin. This is the int A pin. We're resetting the system. 2 pulses. So what I'm going to do is switch back to GlaBIOS, because remember, we were getting like 3 or 4 interrupt pulses on IRQ0 itself. No, but there's our 2 pulses. If I reset the system, just immediately 2 pulses. All right, now hold on a second. Back on the data sheet, people were probably screaming at their screen. It says when the CPU is an 8085, you get 3 freaking pulses. When it's an 8086 or 8088, you only get 2. And it says, when the second int pulse is issued from the CPU, the 8-bit pointer is released onto the data bus. This completes the interrupt cycle and the interrupt routine will be serviced. The ISR bit is reset. Okay, so 2 pulses, what we're seeing is correct. I think what I need to do is hook up a second probe, because when we get those 2 pulses, the CPU should continue doing stuff. And it's my hunch that it's just locking up solid. And we need to figure out why. that's going to be the tricky thing here. All right, so channel 2, the yellow trace, is now hooked up to the signal that comes from the 8288. So when we turn this on, we should get our pulses, and that's also going to be the trigger point. What I want to see is what's the data bus doing, and I'm on one of the data bus pins when I hit the reset on the system. Okay, well, stuff is happening. Zoom out a little bit and do that again. You can see up at the top here, the computer is definitely freezing. It is no longer executing code. Yeah, see here? We get the pulses, and there's a little bit more activity on the data bus, and then that's it. It just goes into this state of nothingness. And every time I reset the system, what we see on the scope is exactly the same. I mean, that red trace, if I lift the probe up, it's going to go away. But back on that data line, looks like that. I'm going to try a different data line pin, so that the information is different, but then it halts. But it's funny because it does execute more stuff, like there's more things happening, and then it gets into that state where it's all weird and down low. Let's check out one of the address lines. Okay, so that's slightly different. It kind of goes into this pulsation thing here. So remember, there's the trigger with those 2 things that are happening, and then it just gets all weird. And you see how it like goes high for a bit with these weird pulses, and then there's more pulses and low, and I don't know, it's just so strange. But all the data lines look the same, and they don't have that weird pulsing behavior. Let's check the data lines on the RAM. Yep, they also have that weird sort of pulsing thing happening on them. I'm going to zoom in a bit. I want to see what that looks like closer up. I mean, that's strange. That's the data line doing that. I almost think that seems like a bus conflict. And let's look at the address lines. So those don't have a bus conflict. They're just doing that weird pulsing thing. And they're not all the same. Like there's this one here that's just high. That one is just low. But yeah, it's the data lines. That looks bad. So it's not like they're totally dead or broken. Like that's, I'm back on what, pin 16? Here's 15. But 15 goes from working all of a sudden to that. And so do the others that have that weird spiky thing going on. So they go from working normally to all of a sudden looking like that. So I really feel like there's something on the data bus that's causing this. And it's getting turned on at some point, like around this point, and it's trashing the bus, which just causes the whole computer to stop working. So far, we're looking at GlaBIOS, BIOS, and there's that weird behavior. Let's switch over to some of the other BIOSes and see if we have the exact same kind of crashing symptom happening. So I'm going to pop over to AMI next, which we know takes a little bit longer before the interrupt is triggered, before it'll freeze up. Oh, so that looked different. It looked very different. So there are the 2 pulses. And here it is, like, well, that's weird. But it's like it continues on like nothing bad happened. So I just reset the system. Our 2 pulses happen. And then, I mean, it's, so the AMI BIOS behaves differently. So it's like something's happening in GlaBIOS after a little while that gets the computer into some weird state that obviously is frozen. There, I tried a different data line. So this one is definitely not frozen. This is the AMI BIOS. I'm trying a different data line now. Yeah. So this is how I suppose sometimes it's able to go, oh, there's an interrupt problem of some kind, because it's not actually totally dead. What we need to do is switch over now to, I think, SuperSoft and look at what that looks like when it freezes. This takes a lot longer to get to that point, just because it's doing all this RAM testing and stuff. Here we go. Should happen in a second. Ah, there it is. Okay, well, it's also not frozen. I just reset the system so we can take a closer look at what's happening there. I'm wondering if the next thing I should do is go to GlaBIOS source code, and we can look at what happens when interrupt 0 is triggered, because that's obviously what's happening when it freezes. I mean, look, it looks fine. I just don't get it. What is it doing right now in this weird frozen state? That's the question. What is it doing? Without source code for both of these ROMs, it's kind of impossible to know like what they're expecting to do right here. Like, is it handling the interrupt? And yeah, what exactly is going on? I don't know. I'm back on the data sheet for the interrupt controller. I just want to see if there's anything I missed. So there are the 2 pulses, and that's not for the CPU we're looking at here. We got to find the section on the 8088 or 8086. So here it is, section 2. The data bus keeps the high impedance state when the first intake pulse is issued. Then the pointer T7 to T0 is released when the next intake pulse is issued. The content of the pointer T7 to T0 is shown in table 3, and this of course is for the 8088, not 8085 like I messed up earlier. The T2 to T0 are a binary code corresponding to the interrupt request level. A10 to A5 are unused, and the ADI mode control is ignored. I'm not sure what it's talking about with A10 to A5 because it says let's look at table 3. Here's table 3. The output is all data bus, so the interrupt request 0 through 7. And then we have the 3 lowest bits on the data bus represent which interrupt was triggered. So interrupt 7 would be 111 and 000 for interrupt 0, which of course is the one that we should be looking at, right? Because we're looking for interrupt 0 right now, which is that timer pulse that's happening every 18 milliseconds. As far as T7 through T3 on the other data bits, what are those exactly? Looking through the rest of the data sheet here, I don't really see that. Interesting. It doesn't explain what that means exactly, unless it's further on here. Perhaps I'll get more information if I check out the Intel datasheet for the interrupt controller. It says for int A, this will cause the 8259 to release the vectored information onto the data bus. The format of this data depends on the system mode of the 8259. So for 8088 system, upon receiving the int A from the CPU group, the highest priority ISR bit is set and the corresponding IRR bit is reset. The 8259 does not drive the data bus during this cycle, so that's the first pulse. The 8086 will initiate a second int A pulse. During this pulse, the 8259 will release an 8-bit pointer onto the data bus where it is read by the CPU. This completes the interrupt cycle, and the AEOI, and I think EOI means end of interrupt, the ISR bit is reset at the end of the second int A pulse. Otherwise, the ISR bit remains set until an appropriate EOI command is issued. That's an instruction in the 8088 code or 8086 code. If no interrupt request is present at step 4 of either sequence, i.e. the request was too short in duration, the 8259 will issue interrupt level 7. Both the vectoring bytes and the CAS lines will look like an interrupt 7 was requested. I think what that's trying to say is that if it gets an int A pulse when there was no interrupt request at all, or it doesn't think there was an interrupt request, then it basically acts as if an interrupt level 7 was issued. When the 8259 PIC receives an interrupt, that would be like channel 0 from the PIT going into the PIC, int becomes active and an interrupt acknowledge cycle is started. That's sort of what we were seeing, right? We were seeing a signal that goes from the interrupt controller to the CPU, and then that 8288 is issuing those int A pulses back. If a higher priority interrupt occurs between the 2 int A pulses, the int line goes inactive immediately after the second int A pulse, and after an unspecified amount of time, the int line is activated again to signify a higher priority interrupt waiting for service. The inactive time is not specified and can vary between parts. The designer should be aware of this consideration. Well, one thing I don't think I did is I don't think I looked at the int signal coming out of the PIC at the same time as the int A signal coming back to it at the same time on the oscilloscope. Maybe we should do that. Let's see if I can find out these tables. Here it is. So 8088 mode is similar to the MCS80 mode, except that only 2 interrupt acknowledge cycles are issued by the processor and no call opcode is sent to the processor. The first interrupt acknowledge cycle is similar to the other system in that the 8259A uses it to internally freeze the state of the interrupt for priority resolution. And as a master, because I think you can cascade multiples of these, it issues interrupt code on the cascade lines. I don't think those were even hooked up in this situation. On the first cycle, it does not issue any data to the processor and leaves its data buffers disabled. On the second interrupt acknowledge cycle, it will send the byte of data to the processor with the acknowledge interrupt code composed as the following. Note the state of the ADI mode is ignored and A5 to A11 are unused in this mode. This is what it said in the other data sheet. And this looks exactly the same. What are these T3 to T7s? Again, I'm not 100% sure. Perhaps what it's talking about when it comes to this A5 to A11, it has to do with the other mode of operation where there are 3 calls, because look, it seems to use these address lines and puts them actually on the data bus. So probably tells that other processor where to go for the interrupt vector, but on the 8088, that is unnecessary. I'm gonna do one more quick test where I'm gonna look at the output of the interrupt controller going to the CPU, that's the int line. And we also have the probe already on the int A line coming from the 8288. I wanna see those together, how they look, where they're interacting with each other. And I currently have this set to use Glab BIOS. All right, well, this doesn't really make sense. So the red trace is the interrupt signal going to the CPU, or maybe it does make sense. Let's zoom out a little bit, because I think on GlaBIOS, what's weird is the interrupt signal that goes to the CPU, which is the red trace, it's very, very long. So there it is, it gets asserted when it goes high, and then it sits high for quite a while. I don't know why it disappeared, the trace, but if we power cycle the computer again, it seems to go low right after the double pulse. So that must just be a normal timing consideration. So the int signal goes high, and then when this double pulse is ready, then the PIC, the programmable interrupt controller, deasserts the interrupt signal going to the CPU. That must be just normal behavior. Why don't I switch over to one of the other BIOSes? Let's switch over to the AMI BIOS, and let's look at what that one looks like. So we turn it on the computer. So for whatever reason, the interrupt signal going to the CPU, the red trace, is much shorter on the AMI BIOS than it is with the Glab BIOS. But either way, it gets deasserted directly after that second pulse. Now, one thing I think I understand better is that the interrupt controller puts one of these interrupt vectors onto the bus as soon as that second pulse happens, like at the end of that second pulse. And we know we should be triggering off interrupt 0, which means if we take a look at data bit 0, 1, or 2, that we should see bits all the way at 0. That's as soon as that second pulse happens. And remember it said, like, if it's detecting something weird happening, it might be issuing an IRQ7, which of course would be 111. And I still don't fully understand what these other bits are doing, T3 through T7. So we'll take a look at data bit 0, 1, and 2. That's 11, 12, and 13 on the EEPROM sockets, because those are the easiest for me to probe. And I'm going to remove the jumper, so we're back on GlaBIOS because it does the interrupt immediately. So we turn it on. Okay, well, my assumption, based on what we saw in the data sheet, is that the bus should go high impedance, and that's probably what we see up in the middle here. And then it's being driven by the interrupt controller itself. And remember, I'm on data bit 0 right now, pin 11, and that's up at 5 volts. Now I moved over to pin 12, which is data bit 1. Reset the system, same thing. And I'm going to check the third bit now. That's pin 13, and that's data bit 2. And again, that's high as well. So if I reset the system repeatedly, and I'm currently on pin 13, so data bit 2, it looks exactly the same every single time. We go back to data bit 1. Again, it looks exactly the same. And now we're on data bit 0. Same thing. Immediately after that second pulse, it is high. Now, what I don't fully understand is what the timing should be. Maybe we can find a timing diagram in here. This is the Intel datasheet that tells us how long after that second pulse it's actually driving the bus. And I think this is the int A sequence. So we're only going to have 2 of these pulses, right? So you get 2 pulses. And remember, this is matching what we saw. After the second pulse, the int line that's being asserted going to the CPU, that does go down. So that's what's happening right there. We saw that. And there's the data bus. And then looking at this, so when int A goes low and that pulse is up, then where's the data bus? This is the data bus. Where is that driven? So this is saying high or low, so it can be driven either direction. And this will be high impedance where it has the dashes. So TRL-DV, data valid from read or int A falling to low. 200 nanoseconds. Or on the A-2 variant, this is not the A-2, this is this one here. So 200 nanoseconds. It seems to indicate that it actually drives the bus on the falling edge of int A, not on the rising edge. And is this right here driving the bus and putting the interrupt vector on it? I was thinking it was this section over here, which always seems to be a 1, but maybe that is not the case. And maybe it's this section here. It's such a short time though. That's 248 nanoseconds. Obviously it's 200 nanoseconds per division. That just seems really, really short. What is this other part, this NEC part? Why don't I swap over to the NEC part and let's just see if that looks any different. I'm partially assuming that this other chip is just going to be faster than the Intel one just because it's a newer part. So right now we're looking at the yellow trace, which is int A, and then the red trace is the interrupt signal itself. So let's go back to one of the data lines. Huh. So that seems different now. What's different on the other chip is in this little section here, let me zoom out a little bit so it kind of looks more like what we were looking at. We saw what looked like the data bus floating in here a little bit. Oh, so there's a little bit of floating there on that one. That is data bit 1. It looks the same basically, doesn't it? And then this one, oh yeah, there's more floating going on there. Now, in case you're wondering that the yellow trace looks too high, that's just because these aren't aligned. So if we align these, there we go. That's more like around ground. This is more like floating. And we should be seeing all 3 of these lower data bits at 0. And that seems to be exactly what we're seeing there. Okay, actually, no, that one is just floating. So that's data bit 0, data bit 1. That one's down at 0, data bit 2, down at 0. Then we're into the data bit 3, which is like those pointers. That one is up high, which might be normal. That one seems like it's floating. That one's at 0. That one's also 0. And this last one, which is data bit 7, looks like it's at 0 the whole time. All right, well, I think I'm gonna have to end this video here. I'm definitely kind of stumped a little bit. It's funny to me that both these data sheets, the Intel one and the Mitsubishi one, are just so vague about how this is actually working. And I'm sure experienced electrical engineers can look at these diagrams and these tables and know exactly where this chip is driving the bus. But to me, it's not really clear. It's clear to me that the 8088 CPU plus that 8288, there's like a whole dance going on between them with an orchestration of how all of this stuff works. And then from the best of my understanding, what happens is when this interrupt sequence happens, this interrupt controller puts the vector onto the bus, which is what we're trying to look at there. The CPU picks it up off the bus, and then it jumps to that location in memory, and it starts executing the interrupt handler, which in this case, if it's jumping to the correct value, it should be running the interrupt 0 handler and incrementing the time of day or whatever is supposed to happen, and then it's supposed to return out of the interrupt and continue resuming code. But obviously we saw this scope with Glab BIOS, at least, it doesn't really get, well, it gets stuck, right? We see that weird stuff that's happening. With the other BIOSes, it does seem to continue executing code, but the thing is still frozen. So obviously it's still crashed. So I think for me, I need to try to get my head around how the interrupt handler is supposed to work. I could probably do these exercises we're doing right now on another working board so we can kind of compare what we see. I also have a logic analyzer, which I'm almost certainly going to have to break out so we can take a look at what's actually happening with the logic analyzer and kind of go from there and just try to figure out what exactly is going on. I honestly felt that replacing the CPU or the 8288 or the interrupt controller or all 3 would have made this machine work, but clearly that is not the case. So when interrupts get triggered, there's something wrong on this motherboard that keeps the system from being able to execute code properly, like the interrupt handler's not working or whatever's going on, I'm not totally sure, and that causes the system to freeze. So that's going to be it for this video. If you have thoughts on what I did wrong here or on what might be going on with this motherboard, I'd love to hear in the comment section about that. Thumbs up if you liked this video, thumbs down if you didn't, all the usual YouTube stuff. It always amazes me when I'm working on seemingly simple things like this old XT clone motherboard and it's behaving in a way that doesn't make sense and I can't quite get to the bottom of what's going on. It's always kind of a fun challenge to fix this thing. Even though I have plenty more of these XT boards, I could just put this one away and never look at it again. That's not the point. It's fun to unravel these mysteries. So that's going to be it. Stay healthy, stay safe, and I'll see you next time. Bye-bye.